This is example number 3 on and 2D potential flow. In this example, this is a very classic problem, and we actually worked on this problem in one of the previous homeworks. And what it says is you have a uniform flow at velocity v infinite, and it has a cylinder radius a. It's centered at the origin and is perpendicular to the axis y, x and y. And what you can see in this problem is what you're given is a potential flow, and you asked to determine if the potential flow is valid. Find the stream function associated with this flow, determine the pressure distribution around the cylinder, and explain the flow behavior. And also stays to clearly state all the assumptions. So let's start to understand this problem. First of all, we have a potential flow, right? Since we have phi, the consequences having phi is that the field is irrotational. And because it's irrotational, it means that the cross product is equal to 0. Also, as a consequence of this, it means that the flow is incompressible. The fluid is incompressible. Okay, which means this dot this, velocity is equal to 0. Okay, and the other thing, we also assume whenever we have potential flow that the fluid is inviscid. By inviscid, we mean that we are ignoring all the viscous effects. Okay, so this is a very popular solution, very popular solution. And the problem is asking if this potential flow is actually valid. Well, to be valid, it has to satisfy these conditions. Actually, specifically, it needs to satisfy this one. Okay, because this condition, okay, the question is if it is valid. There are two ways to prove this. The first way, the easy way, is just to show that we know this is 0, and if there is a potential flow, that means that this exists. So therefore, this is equal to this, and it's equal to 0. Okay? Since this is 0, in polar coordinates, what we have is, this is the equation in cylindrical coordinates. And all we have to show is that this is actually equal to 0, and that will say that the potential flow that we use is valid. Okay, so we know in the problem that phi r of theta is equal to v infinite r plus v infinite a squared r cosine of theta. Okay, so let's evaluate each one of these terms. So the first term is this one right here. So second derivative of theta squared, this is a constant, so it's a double derivative of this, and you can use calculus and show that the value that you will get is r plus v infinite a squared r, and you remains cosine because the first derivative is sine and becomes negative, then sine becomes cosine. Okay, so the next thing you keep in mind here is, let me change the colors quick. I have 1 over r squared, so I have 1 over r squared, 1 over r squared. So then the whole expression will become minus v infinite over r plus v infinite a squared r cubed cosine of theta. Okay? So we got the first expression. So this expression is the expression that goes inside here. Now let's work with this expression. Okay, this expression then, uh, let's work on the next page. Partial of phi respect to r, that gives you v infinite minus v infinite a squared r squared cosine of theta. Then I multiply r, so I multiply r and I multiply r. Then the next it says take the derivative of r phi r, and that derivative will give you v infinite plus v infinite a squared r squared cosine of theta. And then you have 1 over r, and you have 1 over r and r. So now we put it all together inside this equation. Okay, take this on the next page. Okay, so now we plug everything inside here. This expression gives you, the first expression gives you uh, v infinite r plus v infinite a squared r cubed cosine of theta. And the previous expression is the same but has a minus sign. So it's minus v infinite r plus v infinite a squared times r cubed cosine of theta is equal to 0. This gives you 0, so 0 is equal to 0. That means a valid field. Now there's a second way to do this problem. I am not asking you to do it, but I want to discuss it so you at least have an idea how this is done. Many times we actually don't have this function at all. We don't have it. We want to find it. So the other option could have been, let's find what the function is, and if I get the same value, then that's the function. So in that context, let's go and start from the, and again, you don't have to take notes on this. Um, the purpose is basically to outline how you do these problems. So you will have this problem, okay, and this is actually, we know that this has to be 0. The idea is to use separation of variables. So we want to say, is it possible to express this, a function strictly in r, a function that's strictly in theta, let's say, okay? So in that sense, we plug this in here and we can decouple your equation. So what happens is now I can say all on one side can be theta and all on one side can be r. Okay, as you can see, a function of theta and a function of r. And since this is equal to this, I can go ahead and say this whole equation has to equal to something. Okay, so rewrite it and we can write this whole equation equal to a constant k, which we will find it later. So now the process is that two differential equations, one will come with this, the second one will come with this and this, okay? So we got two equations. The first one is this with this, and the other one is this with this, okay? That's a differential equations. It's not intended in the course that you have that knowledge, but I'm just going to go ahead and give you the answers anyways. If my value n is equal to 0, so this is the solution. If it's not 0, this is the solution to this differential equation. To this differential equation, these are the two solutions you have when n is 0 and n is not equal to 0. Okay, so I combine everything. You can show that the total solution now is equal to this. Okay, so now let's go ahead and start working on this. Now, what we know in the problem, if I'm working in the far field, as I'm way large here, right, in the far field, you know the R is way bigger than A, right? Your R is way bigger than A, so you're saying that a value of R over here in the far field, the flow has to be uniform. has to be in the x direction. So we know it has to be sigma sub 0 is equal to v infinite r. And this actually, where does this come from? This comes from the fact that your v is actually equal to the gradient of phi, right? If that is true, then the derivative, partial derivative of this respect to x goes away, okay? And that gives your velocity. That's what this is x. Now this comes here from your cylindrical coordinates that we know x is equal to r cosine of theta. So hence, when r is very large, all these terms actually go to zero, okay? Because you have 1 over r, and if r is very large, that will go to zero. So I could ignore this term at the beginning. So I can now go ahead and I have this term. For a very large, I eliminated that term. So I end up with these terms now. So the other thing that we have to know in the problem is that if I say this, right, so I can show that my value phi will be, and I kind of give you the derivation here, like I told you in the previous page, right? So it's going to v infinite r cosine of theta. We equate these, right? But note that these are all constants, and either one of these constants here actually gives me cosine of theta. So immediately right here, you could say, you know what, this whole term has to be zero. So this can only be zero, all of these terms are zero. Okay, so then we keep simplifying your equation. And the other thing I could do is I can say for n equal to 1, if I replace n equal to 1 in this equation, so n is 1, 1, 1, 1, only 1, okay, the first term. So you said this is equal to this. You can see that A1, C1 is equal to V infinite. Okay, so we could do that. And if I extract the first term from here, you can show that your further equation can be simplified to this. Okay, so I'm just trying not to go in nitty-gritty details into this, just to give a higher level how this is done. Also, we know, if you remember from your class, we don't want the fluid to penetrate. We don't want the fluid to penetrate the cylinder. We want it to go around the cylinder, right? If there's a stagnation point, it stops right there. It doesn't do anything. But if it goes around that, you have to flow. It cannot go inside. So if it cannot go inside, we know that this boundary, right, has to equal to zero. In other words, v infinite times er, or partial of this of r has to be zero. This is whole equal to this. If I take the partial derivative of r, we can show that this is the expression you get. Now, the whole thing here has to be zero, okay, because of this virtue when I say r equal to a. So I put r equal to a, okay, and all this thing has to be zero. The only way this is going to be zero if this whole thing is zero, a and b. So this goes away. I'm just end up with these terms now, okay? So I'm going to solve for a. So I solve for a, and I find a is equal to v infinite a squared. I replace it inside there, and you replace it inside your original phi, that's here. This expression, replace a here, then you find that this is the expression that we started with. So this is the second way you can show this problem. You can show that this is the functions that you're looking for. Okay. Now your problem is also asking to say what are the stream functions. So we know that your stream functions are given by partial of phi, partial of r, is equal to 1 over r, partial of psi, partial of theta. And we know that 1 over r, this is ur, this is u theta, is going to equal to partial of phi respect to theta. This will be minus partial of psi respect to r. So what we're going to do is we're going to take an equation and we will take the derivative of phi respect to r, and we're going to take the derivative of phi respect to theta. And let's see what we get. This gives you VRB minus V infinite A squared R squared cosine of theta. This will give you VR, this is minus, V infinite A squared R sine of theta. Okay, so we found this, and this one has a 1 divided by r, so we can divide this expression by, let me change the colors, divide this by r, so that means this is divided by r, this is multiplied by r, so this whole thing then becomes minus v infinite plus v infinite a squared r squared sine of theta. Okay, so this is your UR, this is your U theta. Those are the velocity vectors that we are looking for. Now we're going to set the velocity vector to this, and you're going to find psi, we're going to find this one individually. Okay, let's do that in the next page. So this is the equation that we have. Now we take this r, multiply r on both sides. So we have r's on this side. So, and we're going to integrate in theta. Okay, so we integrate, we find that psi is going to equal, on this side, your psi will be v infinite r minus v infinite a squared r sine of theta plus a function in r. Okay, because when you integrate in r, you will get the other variable. Remember, this is going to be a function in r and theta. So if I integrate in theta, the function I'm left with is r. And then this side, minus minus cancel out, and I integrate respect to r, and I find, okay, so psi is equal to this. And this will be a function in theta. And you can see that this function is identical. So your function of r is actually here. Your function of theta is there. So therefore, we can conclude from these two that fr and f of theta are actually equal to 0. So you can say that your stream function that you're looking for, your stream function number 2, this is going to be v infinite r minus v infinite a squared r sine of theta, or we could write it as v infinite r 1 minus a squared r squared sine of theta. Okay, so this is the value of this function, and the stream function, number 1 has to be z, because we are has to be perpendicular to the flow. Okay, so far so good, right? So next item that the problem is asking you is saying, so we got the potential flow, we got the stream functions, determine the pressure distribution. So to find the pressure distribution, we will use the Bernoulli's equation. Pressure distribution. Just remember, I can use Bernoulli. I'm going to use Bernoulli's equation, because Bernoulli's equation applies when the fluid is inviscid, is irrotational, right? And that is how we have the fluid anyways, because I have a potential. So we have in your problem, we know that your pressure is actually equal to 1 plus rho times velocity squared times your stream velocity, that would be 1/2 rho v infinite squared. Okay, so if I want to know what my total pressure is, I just need to know, I want to know what my P minus P is. It's a lot easier to understand what this happens. So this will give you um, uh, 1/2 rho v infinite, and we did this in class. 1 minus v squared over v squared, v infinite squared. Um, so then I can define my pressure coefficient, and it's a lot easier to plot or understand what happens with a non-dimensional quantity than it's with a dimensional quantity. So this is easier to do it like this. And now what you can realize is what is my v squared. Now note that your v squared, if I look at the vectorial notation, is nothing else than vr squared plus v theta squared. Okay? And note that we found v theta, right? We found ur and u theta. Well, I call it u, so let's call it u and u. Okay, that would be my v. So if I plug that values in there, okay, you will see that you get the following. So the pressure distribution, as we know, is equal to this, right? So I went ahead and did all the expansion for you. So if you do this and you further, this is a square missing here. You can, take a screenshot of this if you want to. And you do live with mathematics, so divide by v infinite on both sides. This is just this term here, and then I divide by v infinite and do libre mathematics. You can see that this term becomes 1. These two terms, then you have these two terms and these terms, they can be combined. If you can do a little bit simplification, you can show that the end result of your CP is equal to this. These are some nice results that you're going to get. And what you realize here, this is a plot of your pressure distribution, which I really wanted to discuss with you. Because what this plot is saying, that if you realize at the surface, but this is where I really care, on the surface, what happens at the surface of my body, not what happens in the far field. I'm really cared for here, not inside, but over that. That's typically what we do for airfoils, right? So when R is equal to A, right, then R is equal to A, then this expression simplifies to this. And now when this is equal to theta is equal to 0, then cosine of 0 is 1, 2 minus 1 is 1. Theta is equal to pi, 2 times pi, cosine of 2 times pi is 1, so it also gives you 1. So you can see that the pressure in these locations is actually equal to 1. And then the pressure on the top surfaces then would be theta equal to pi over 2, you would, and pi over 2, that gives you 0. So Cp is equal to -1, and this is equal to 3 pi over 2. So this gives you, I'm sorry, this gives you -3. Cp gives you -3. Because when it's pi over 2 is pi over 2, this cancels out, this becomes -1. 2 times -1 gives you -2, -2 gives you -3. Same thing here. Okay, so this point here is 1, this is 1, and this would be -3 where you have negative pressure actually. Okay, so you can see this is a location of maximum pressure. The flow is giving more pressure here than goes there, and this is actually negative pressure. This is what it's really trying to say. And what it's trying to say is that this location here is the location, these two locations is the location of low pressure. Okay. Now, the other thing you can keep in mind, if you want to find the stagnation points, remember that we want a full understanding of what's really happening here. Stagnation point is the location where your velocity vector is equal to 0. So it's the location where your this is 0 and this is 0. Okay, so we know in a problem that UR is equal to V infinite 1 minus R squared sorry, cosine of theta is equal to 0. So this would be 0 when this is 0 or this is 0. And from here we can show this gives you plus minus A. And then what you can also see is that theta is equal to V infinite minus 1 plus R squared A squared R squared sine of theta. And this cannot be 0. This is only this can be 0. And this is 0 when theta is equal to 0 or is equal to pi. So that kind of makes sense in the problem if you look at what's really happening with the flow. Let me just plot the flow around this. Just give me a moment. So if I go to the next page and I was able to show you what the flow looks like, your flow looks like something like this. Um, these are your streamlines that you can see here, right? And you can see that your flow comes here. This is your velocity field, sorry. This is the velocity field. You can see that velocity field is almost constant as you're moving forward, but when it gets closer, this velocity field is actually bigger, but when it gets closer to this point, there's no vectors because your velocity at those points is actually equal to 0. It makes sense, right? So these are the applications of potential flow. There are all sorts of stuff we can do. We can greatly simplify the problem if we are able to do that. Okay, so this concludes example 3.